Hi everyone, my name is Wensheng Song from PROS, and many thanks to Deep Learning AI and Houston Machine Learning meetup for this opportunity to let me give this presentation. So today I will introduce explaining black box machine learning. And this slide is actually just like for those who just joined, because I have already made this introduction by myself, right? So this is just like a quick introduction by myself. My name is Wensheng Song, and I'm originally from China. After I got my PhD in physics from Washington University in St. Louis in 2019, I joined PROS and worked as a data scientist here now. My previous research experience was focusing on computational condensed matter physics, including density functional theory and nonlinear optics. And right now, I'm mainly doing data analysis and machine learning, including deep neural networks and some AI stuff. Also, I'm a trained MMA fighter and a blue belt in Brazilian Jiu-Jitsu and a dad of 2 cats. So for this talk, let's first do a quick recap, right? Last time, I think on this series, Yan has introduced some interpretation methods for glass box models. They are mostly model-specific interpretation. We can clearly see that there are 2 major disadvantages. First, of course, the model-specific interpretation is usually bound to one model type, and it will be difficult to switch to others. And the second one is, under such interpretation, the glass box models cannot be too complicated. For example, it might be easy to explain a short decision tree, right? But what about a very deep and fully expanded tree, right? What about an ensemble of trees like random forest or gradient boosting tree methods? So it is pretty obvious that the model-specific interpretation method have their limitation. And today, we will take a step further to explore some methods explaining black box models. Since it is black box, the explanation and the interpretation should be model agnostic. Last time for this part, we have mentioned some global methods such as sensitivity analysis and partial dependence, as well as some local methods such as the so-called line and SHAP. And this time, we will mainly focus on them and try to dive deep. And before introducing the specific methods, let's think about some high-level questions. What is a black box model? What kind of information we can use if we want to explain them? Usually, black box model is not transparent to us, and we don't know what's in it and how it works. So model-specific interpretations definitely don't work here. However, we still get access to one thing, which is the input and output. And with all those information, we can use the so-called example-based methods. Those methods are mostly model agnostic because they select instances of datasets to explain the behaviors of machine learning models, or to explain the underlying data distributions. Because they don't rely on the inner structure of models, they can be used to interpret all kinds of models, including black box and glass box. Example-based explanations provide us a strategy to interpret the black box, or maybe all kinds of models. Based on that, lots of methods that don't rely on specific models have been developed, and we call them model-agnostic methods. According to a paper in 2016, for this type of methods, they should have some degrees of flexibility. The very first one is model flexibility. Well, that means the interpretation can work with any machine learning models, such as linear regression, random forest, or deep neural network. Second is explanation flexibility. It means that the form of explanation should not be limited. You can use formula, plots, graphics, etc. to explain the model-based on different scenarios. You can focus on positive or negative evidence. Also, you can have different levels of granularities for different situations. And the third one is representation flexibility. So the explanation system should be able to use a different feature representation. This is important because many of the features are not interpretable by themselves, right? For example, in the language processing, right, we have this like embedding vectors for words. Even you have an interpretable model trained on embedding vectors, people still cannot understand the output. But for model-agnostic models, they should be able to generate explanations in terms of words. Now, let's take a look at the bigger picture of model-agnostic interpretability. The lowest layer is a word, right? We observe everything in the world and just pick those we have the most interest in. Ultimately, we want to learn something about the world and interact with it. So the second layer is the data layer, right? In this layer, we will digitize the world to make it processable and storable by the computers. For example, we can have like images or videos or like text and tables at this level. And the next level is the black box model. It is the model-agnostic machine learning algorithms trained by the data. And next layer is interpretability layer, which can help us to deal with the opacity of machine learning models. So it can help answer the questions like, what is the most important features, or like, what is the contribution of different feature values? And of course, the final layer is human. So human is the ultimate customers of the explanations, and the model need to present the understandable information to different people. For example, suppose there is a model trained in diabetes data, and it gives the name or code of the most important genes to me. Well, I mean, personally, I cannot understand it because I don't have such background knowledge. So is this model interpretable to me? Right, maybe not, because I don't know anything about that. I mean, even try to give me some useful information. But a diabetes specialist may find this information super useful, right? Because like he knows like what is the meaning, or what does it represent. So actually here the model is interpretable to him. So in a word, we capture the word by collecting data and abstract it further by learning to predict the data with a machine learning model. Interpretability is just another layer on the top that helps humans to understand. This big picture also helps to understand the difference between the statisticians and machine learning specialists, right? So for statisticians, they usually deal with the data layer, skip the black box model, and directly use interpretable models on the data. And machine learning specialists, right, on the other hand, they usually skip the interpretable models and directly give people the prediction of black box models, such as like deep neural network, right? Sometimes you can say like people say, hey, we achieved some very good results about this, like using this like a deep neural network, but they don't give you any kind of explanation. They only give you the numbers or the results. So I think it is a great, it is very great that like this interpretable machine learning methods can actually fuses the works of statisticians and machine learning specialists together. And model-agnostic interpretation methods can be further distinguished into global and local methods. They have very different granularities. Global methods describe how features affect the prediction on average. In this talk, we will cover the partial dependence plot, permutation features, and sensitivity analysis for global methods. But on the other hand, local methods aim to explain individual predictions. So we will include two methods here, line and SHAP. There are some pretty good resources for your reference and I will mainly cover the contents and use examples from them. To begin with, we will take a look at the partial dependence plot, aka PDP. So the partial dependence plot shows marginal effects of features, usually just like 1 or 2. Why only 1 or 2, not 3 or more, right? We will answer these questions later. And the calculation of partial dependence is very simple, right? For the target feature or the feature of interest in set S, we call it XS. We just keep their values and marginalize over all the other features in the set C, which is SC. And eventually, we will get a function that only depends on the features in S. In practice, we will use Monte Carlo method to calculate this marginalization. So Monte Carlo methods was developed in 1940s, used to study neutron diffusion in nuclear weapons. Basically, you can understand the Monte Carlo method as repeated random sampling to obtain some numerical results. So here we randomly sample the training data to calculate the average. So if the XS is categorical, we will not use a random sampling. Instead, we will force all the data instances to have the same category. Right? For example, if XS is a feature of season and the value is summer, we will replace the season of all the data to be summer and average the predictions. Here are some examples of the PDP plots. Right, we use bikes rental dataset, and we fit a random forest to predict the number of rental bikes. For numerical PDP, you can see the dependency line between the prediction and the different features like the temperature and humidity. And they make a lot of sense, right? Since when temperature is too low, right, people don't want to ride outside. And also, it's actually risky if you have this kind of ice or raining. And also too much humidity and wind will be risky to ride. So the number of rental bikes will decrease. We have a large number of humidity or temperature. And for the feature season, right, since it is categorical, right, we will have histogram plot instead of line plot. And besides, we can generate the PDP plot for 2 features simultaneously, as shown by this heat map on the right. Right. For example, this is actually the cancer probability versus age and the number of pregnancies. And from here, we are ready to answer the previous question, why the target features can be only 1 or 2 for PDP. You can see for 1 feature, we can have line or histogram plots, and for 2 features, we will have 2D heat map. But with 3 or more, it will be super hard to virtualize it, right? Because the feature space will use up all the 3D dimensions. So usually for intuitive plots, 2 features are the upper limit. Furthermore, for each feature, we can calculate the feature importance based on the PDP plot. Right? It is easy to find that for numerical features, the feature importance is actually defined as the deviation in PDP plot numbers, right? But for categorical features, it is actually defined to give a rough estimate of the deviation. And that makes perfect sense, right? Because a flat PDP line usually indicate weak dependence or correspondence on that feature and vice versa. Partial dependence plot is very useful tool to explain black box models, and it is very intuitive and easy to implement. So if you have some programming or data science background, I think it should be easy for you to quickly understand it and write your own PDP method. And that's why we put PDP as our first method in this introduction. Besides, it will give a causal interpretation between the features and predictions. However, there's still some disadvantages of PDP. right? The very first one, as we just explained in the last slide, is a maximum number of features, right? You can see it is very hard to explain more than 2 features. And the second one is actually the biggest problem of PDP. Well, that is PDP is assumed that the features are independent. For example, if you want to predict how fast a person walks, given the person's weight and height, right? It is just very unrealistic for you to average all weights. If the person has a height of 2 meters, right? Because we all know, like usually for 2 meters people, they will not weigh under 50 kilograms. And the third one is PDP sometimes hides heterogeneous effects, right? It seems hard to understand, but let me just give you an easy example. Some people like eating spicy food, some people just don't. Maybe for one group of people, the spicier the food, the better the taste. But for another group of people, right, more spiciness will lead to less preference of the food. So right now, if you mix those 2 groups of people together, right, the same number of just like two groups, right, just measure the food preference versus the spiciness using PDP, you might get a flat line since the preference of these 2 groups of people will cancel with each other. So even we know spiciness is a very important feature for food preference, we cannot see it from PDP plots. And finally, to use PDP, you can implement your own methods, as I suggested in the first slide, or using some existing package that will be the easiest way to do that. For Python, we have this like PDP box in sklearn, and we have this Interpretable package. And for our package, there is some module called IML, PDP, or dialects. And the idea of permutation feature importance is quite the opposite. Instead of fixing one feature, it will measure the importance of a feature by calculating the increase in the model's prediction error after permuting the feature. This idea is actually still simple and straightforward, because if a feature is very important, the predicted value should rely on it heavily, and the shuffling and permutation of this feature will certainly increase the prediction error a lot. And it is even easier to implement than the PDP. You just simply estimate the error, right, with whatever metrics you like. For example, the mean squared error, mean absolute error, or something like that, with your model on the original unshuffled data. Then for each feature, you just shuffle and permute the values to get a new error. Of course, you can do it many times to get the average or standard deviations of all this error. And you just like calculate the feature importance using the permuting error over the original error. So there's another question about whether you should perform the permutation feature importance on training or testing data. Due to overfitting problems, sometimes training data will falsely emphasize on some features to make predictions. And maybe those features are not that important in the test data. But still, I would say it depends on scenarios. Sometimes you just want to test the model and you're aware of the overfitting problem. So you can definitely use the test data. But sometimes you have already eliminated the overfitting problem, or maybe you just care about what feature has the biggest impact on the output to a certain data set. So you don't care about the model or something. Then it is not a big deal, right? So although most of the time you should perform permutation feature importance on test data set, if you know what you're doing, you can still do it on training. And still, right now we just want to say this like bicycle rental examples use the feature importance. So we get the feature importance in predicting bike rental numbers. We can see the temperature is definitely the most important features. Meanwhile, whether it is weekday or weekend or holidays seem to have less feature importance. And a good thing is you can see the deviation for the importance. A large deviation may indicate this feature, the prediction is not that stable. Now, let's take a look at the advantages of permutation feature importance. It is still a very straightforward method, easy to interpret, easy to implement, and it will give a rank of feature importance without retraining the model. And the disadvantages are very obvious. First, you need the true outcome, and it is not always the case, especially for unlabeled data. Also, the permutation will add a lot of randomness to the measurement. Sometimes you need to keep repeating, shuffling, and take the average, and it will take much more time. And sometimes it has the same problem with previously introduced PDP, that the random shuffling of data could create those unrealistic instances for correlated features and adding a lot of bias. There's another feature of this method, which could be both advantage or disadvantage. Permuting the feature could destroy the interaction effects. If two features co-contribute to the output, the calculated feature importance could be low for both of them. Also, if two features are correlated, the importance could be missed. Let's assume an extreme case, right? If you just duplicate the most important feature as a new feature and fit the model might use only one of them, or together like half-half or any kind of ratio, right? It will still give the same prediction power, but when you measure the feature importance, you might see one of them is very important, another one is not, or maybe both of them are not that important, so 5 to 5, or any kinds of numerical results. So it is definitely not very intuitive since both features are exactly the same. They should have the same feature importance, but those results do tell you how the model utilizes those features. Lastly, if you want to use this method, there is sklearn, alibi, and IFB-IMP in Python, and IML package in R. For the next part, let's talk about the sensitivity analysis. Well, actually, this is a very large topic covering a wide range of areas, especially in engineering. And it has been applied in practice long before the appearance of machine learning or AI. Since I'm not very familiar with this, I will just go through some conceptual stuff and a few methods. So in one line, sensitivity analysis is a measure of how sensitive a model is to the changes in parameters. For example, if you change one of the features, how much the output will change. It sounds like partial derivative is a good measurement for this, but that's local sensitivity instead of like global sensitivity. There's a very good YouTube video introducing all those methods, and I put the link in below for your reference. For global sensitivity, we will introduce two methods here. The first is derivative-based global sensitivity measures, DGSN. You can clearly see in the formula that it tries to calculate the variance of the partial derivatives of one features. And of course, you need to select the appropriate delta x and integration region for this calculation. And this is actually very similar to the previously introduced partial dependence calculation. And just like partial dependence, here you can use an approximation to improve calculation efficiency called Morris one-at-a-time method. Instead of calculating all the partial derivatives, it will choose one feature or direction to move a fixed step every time and calculate the derivatives for each features. As you can see here, for the two features and the three features cases, right? Every time you move the same step in a different feature directions and repeat this process many times. Right, here's the output of the Morris method. As you can see, it will output the single values for each features. Of course, because of the randomness, you can run it multiple times and calculate the mean and deviation of the feature importance, just like the permutation feature importance. Morris method is very fast, yet it cannot deal with interactions as well. So if you want to use this method in Python, there is a package called SHapley and some other packages based on the SHapley, such as Interpretable. And for R, there is a method called Morris to directly perform this. So here, all the previous introductions are about global methods. And as we can see, all the global methods simply tell you which feature is important or how does it contribute to the prediction. But it cannot tell you more granular things. And for example, if we want to know or we want to predict the joint injuries, right? We try to fit a model and the model will tell us, hey, age is very important feature. But what is the difference between an age of 20 or 60, right? We are younger age lead to a lower possibility of joint injuries, right? We simply don't know that. To answer these questions, we need local methods, which explain all those features for each individual instance. For example, there's a guy, 20 years old, male, lifting weights 2 hours a day, etc. Like it has a lot of different features, and we want to know the contribution of all those features to his joint injuries risk, whether it is positive or negative, and how much. And what's more, most of the time, those features will interact with each other and co-contribute to the prediction. And that's extremely hard to determine at global level. For example, for 20 years old people, maybe I would say lifting weights will help you get a lower risk of joint injuries. But for an 80 years old, male on a wheelchair, maybe it is not a good idea. But what if in this 20 years old guy, he has some kind of old joint injuries and his joints are very fragile, right? It is actually very complicated scenarios. That's why we need local methods to deal with this. So we will start with local interpretable model-agnostic explanation, aka LIME. In my understanding, LIME is using an explainable model to explain the target instance with neighborhood instances. Here is an example showing how it works, right? You can see here's a toy data with 2 features. Each data point is associated with a ground truth label. Black is positive and yellow is negative. And of course, in this plot, the decision boundary between the positive and negative are curved. So we need some nonlinear model, such as a random forest or neural network, to classify the points. Suppose we have a black box model doing a really good job here, like this, and it predicts all the points in dark gray area to be positive and light gray area to be negative. Now we have this purple point as our point of interest, and we want to know why it is classified as negative by the model. So LIME method will find some random data points and assign weights to those points based on their distance to the purple point of interest. As a result, closer points will have more importance in LIME, indicating by the size of those dots in the picture. For the point of interest and its neighborhood points, LIME will use a very simple yet explainable model, usually a linear regression, as a local surrogate model to fit them. For example, here's a local surrogate model identifies the purple lines as local decision boundary. The linear model has coefficient as feature importance, and it will tell you why the purple point of interest is predicted to be negative. If you choose another point of interest, then there will be a different linear model give a different set of coefficient as feature importance. And those feature importance can serve as a granular explanation for different points of interest. Here is a good example of output generated by the Python package LIME. Right, the first one is for tabular data, basically for a given instance. or point of interest. It can be used on both classification and regression, and the output actually looks very similar. Right on the left, as you can see, it tells you the prediction results. Right, it could be like probability of classification or numerical values for regression target values. Right, and in the middle, it will tell you the contribution of different feature for the prediction, which is the coefficient of the local linear regression models. And on the right, it is the value of different features for this instance. And LIME can also be used to explain text classification. As you can see, it will highlight the most important words and their contribution for the classification on the right. And what's more, for image classification, LIME can highlight certain areas of images to tell you which part helps to determine whether it is cat or not. Finally, if you want to use LIME, there is a LIME package for both Python and R, and I think this method is included in the Interpretable in Python. As a local model agnostic method, LIME can definitely generate explanation for different levels of granularity. It can give individual explanation for any given instances, and the summation of all the instances will give you global feature importance. Another advantage of LIME is that it can work with multiple forms of data, such as tabular, text, and images. Also, if you have the flexibility to choose different surrogate models, right, you can choose like linear regression, right, this in our example, because it can directly give the coefficients as explanation for different features. I would say still, like any kind of models that can give you feature importance can serve as a local surrogate model, such as a short decision trees or even a neural network. I mean, as long as they can give you the feature importance. But this flexibility could be a disadvantage for LIME, right? If you choose a too simple local surrogate model like linear regression at some complicated decision boundaries, this model cannot capture them, and it will lead to unstable predictions. If you use complicated nonlinear models to deal with those situations, it will have overfitting and efficiency problems. In a word, there is not a single form of local surrogate model that can take care of everything. You always need to sacrifice something. It is very similar for choosing the right neighborhood, right? What is a good size or good sampling method to capture those like proper decision boundaries, right? It could be different for different points of interest, and you cannot tune it for every one of them. In practice, you can easily manipulate the explanation by choosing different hyperparameters, such as the size, sampling method, the local surrogate models, and it will definitely harm the reliability of LIME. And finally, we will introduce SHAP. So SHAP is actually the abbreviation of Shapley Additive explanations. It is different from the Shapley values. I have seen a lot of the confusion between those two terms, and right now it is a good time for clarification. So Shapley values is a mathematical method for collision game theory introduced by Lloyd Shapley in 1951. And it tells us how to fairly distribute the payout among different features. In the meantime, SHAP is a numerical method that uses Shapley values to explain individual predictions. It was introduced by Lundberg and Lee in 2017. And it has evolved into different forms of the so-called explainers in the SHAP package, which integrated with other techniques, such as we have this like kernel SHAP, which is LIME plus SHAP. And we have tree SHAP, which is specially designed for tree-based models, and deep SHAP, which is deep lift plus SHAP, designed for deep neural network. The later two semi-model agnostic methods think they only work on certain types of models. And there are still other SHAP explainers for different scenarios, and all those explainers are included in the SHAP package. So if you can say that SHAP is a computational implementation of Shapley values, and the relationship between them, like the backpropagation, multi-layer perceptions, and the deep neural network built on TensorFlow or PyTorch. And we first take a look at the Shapley values. It will help us to determine the payout on the collision. It is not a trivial problem because usually the cooperative contributions of the features are not additive, right? Today is a National Cheeseburger Day, so I will give you a special burger example. Right? For example, I work in a restaurant and I order a cheeseburger, right? With bread, vegetables, patty, and cheese. And the price is $10. Well, it's okay. I have no problem with that, and I want to pay $10 for this cheeseburger. But today they just tell me, sorry, we are running out of cheese, right? Because today is the cheeseburger day, and everyone wants double cheese. So do you want to have it without cheese for $9? I think maybe fine, right? I'm not a big fan of cheese anyway, so I will take it for $9. However, does it mean if the restaurant just like serve me with one slice of cheese and I'm still willing to pay $1? Of course not, because this is not what I order. This is not what I want, and I don't pay anything for that. So how can you measure the contribution of cheese based on the price I'm willing to pay for that? Shapley value is designed to solve such a problem. It will average the marginal contribution of a feature value across all possible collisions. And in the formula, it will calculate the difference of prediction with and without a certain feature and do a weighted average. Let's still look at this like burger example, right? It looks a little bit dirty, but it's just like a middle school level math. We have 4 components for a burger, which is bread, right? We use the letter B to represent it, the patty P, vegetables V, and cheese C. And I have a table of all these combinations of those 4 components, as well as the price I'm willing to pay for them. For example, I'm willing to pay $10 for a burger with all 4 components, which is BPBC, but maybe only $4 if it is only bread and patty. So like the BP is just like $4. And with the formula and the table, I'm trying to calculate the contribution of the cheese C. We go through all these combinations with C and without C and calculating the difference, as well as the factor using the size of existing subsets and all components. And finally, I get the contribution of Shapley values of cheese, which is 12/12 equals 1. Following the same procedure, I will calculate the Shapley values for P and B and V. And we can see patty and bread have the same Shapley values and cheese has a less. Adding them together equals 10, which is exactly the price I want to pay for a full burger BPBC. From this example, we can see that the Shapley values not only consider the collision, but also add up to the prediction value. So it will be an ideal method to analyze the contribution of different feature values to the prediction value for a local instance. The burger example is a good exhibition of using Shapley values to solve a general collision problem. But this general form is not a good fit for all machine learning models. Why not? Because in burger example, we can easily remove individual components and give a prediction. But for the machine learning models, all the input is fixed shape. And you cannot just remove columns or features and let the model predict. If we want to predict on a subset of features S with machine learning models, we will do the same thing with previously introduced partial dependence, which is to keep the features in S and marginalize the features not in S. For example, if S is feature 1 and 3, we will marginalize on the feature 2 and 4, just like PDP. And this marginalization is an integration and requires numerical approximation to get the value efficiently. Also, the combinations of different features will explode. If we have a large number of features, for example, 20 features, there will be more than 1 million combinations, which takes forever to run. So some treatment or approximation are needed to implement the calculation in real time. For example, there is a Monte Carlo sampling. Basically, this method will randomly select a sample instance and hybrid with the instance of interest in 2 new instances. One will keep the selected feature and one will replace it. And then we calculate the marginal contribution of these 2 new instances as approximation for the Shapley values of the selected features. Now let's take a look at how SHAP deals with the application of Shapley values. Right, Shapley values, SHAP values are Shapley values of conditional expectation functions in a linear model with an additive feature. You can see in the formula that the phi j is the Shapley values for the feature j, and z prime is either 0 or 1 to indicate if a certain feature exists. So for tabular data, all z should be 1, and it is exactly the same with Shapley values definition. The key here is how should we estimate these conditional expectations fxs. Of course, it can use a sampling method as introduced in last slides, and it is just another implementation of Shapley values. In my understanding, the biggest innovation of SHAP is how it calculates the expectation values. There is a model-agnostic kernel SHAP method to use line estimating SHAP values, which is brand new idea in their paper. So what it does is to replace the weighting of instances in line with the SHAP kernel and the calculated coefficients of the local surrogate linear regression model will be the SHAP values we want. And there are also two model-specific SHAP methods, which are tree SHAP and deep SHAP. I would rather call them semi-model agnostic instead of model-specific, because you only need to determine the general model type and the package you use, and the final explanations have nothing to do with the model. Tree SHAP works for tree-based models such as decision tree, random forest, gradient boosting tree methods such as XGBoost or LightGBM. Essentially, tree SHAP will take advantage of tree structures to estimate the conditional expectations super fast. Tree SHAP has been integrated with XGBoost and LightGBM and made to run even faster. And deep SHAP works for deep neural network implemented in TensorFlow and PyTorch. And it will use the rules of deep lift to approximate Shapley values. Deep lift is a backpropagation method to find the impact of different features on the output of deep neural network. So this method requires all the input of instances to be numerical. If you have categorical features in your input, it will be better first embedding them into vectors. For those methods, I will not get into details. We just need to keep one thing in mind, that they are all trying to calculate SHAP values with different approximation methods. If everything works perfect, in ideal case, the SHAP values calculated by all methods should be very, very similar. Here is the most straightforward examples of SHAP values for just one instance. Right on the top is a waterfall plot, and it will tell the SHAP values or the contribution for each feature values. All those values, as well as the baseline, add up together to be exactly the output. In this example, you can see the age equals 65 has a positive contribution 0.4 SHAP values, which is red for this instance, while the sex equals F has a blue negative 0.3. There's also another plot called force plot, which is just a variation of waterfall plot, putting all those contributions of features in the same line. It still gives the same kind of information. And SHAP can deal with text problems. For example, here is a sentiment analysis of IMDb movie reviews fitted by PyTorch BERT. SHAP can highlight the positive and negative text, such as words and sentences, and tell you how much do they contribute to the output. And SHAP can also deal with picture classification problem to tell which part of the picture plays the most important role. In the plot, you can see SHAP tries to explain why handwritten digits are classified into different numbers. For example, you can see here, the third handwritten digit is labeled as 0 because it's circular shape and empty inner side. And the fourth handwritten digit is classified as 4 rather than 9 because the top part is missing. As we introduced before, you can always summarize local individual instances and get different level of interpretation granularity, such as feature importance and dependence. Here we take the soccer players' score data, for example. Right, we have already introduced a force plot to explain one single player. So we can see his potential is the biggest positive contribution, but his young age could have a negative impact on his score. And we put Shapley values of all players together in a B-swarm summary plot. As you can see on the left side, it gives the SHAP values distribution for each values, features. For example, potential definitely has a positive relationship for SHAP values, but it's not linear. And the long tail in the red side indicates that the high potential could give large SHAP values, but low potential will not harm the SHAP values too much, as shown by the left blue clustering. And for age, it is more interesting. Although the SHAP values roughly have a positive dependence on age, if the player is too old, the SHAP values will be much negative, as shown by the far left red dots. And you can see this plotting in the plot of the SHAP values distribution of the single feature age. All those explanations by SHAP values are reasonable and combine both global and local insights. And of course, if you just want a value for feature importance, the mean value can give you that. It has similar power compared to PDP or permutation feature importance. But of course, it is more customizable. If you want to see the final outputs, considering both positive and negative values canceling each other, the mean value are good enough. Or if you only care about the absolute contribution, you can calculate the mean absolute values. And there are plenty of other plots of SHAP represents the different interpretations. For example, in a decision plot, the SHAP values of each instances will be connected by lines, and you can use those to find similar instance or do clustering. Similarity measurements are made easier by SHAP values because the input could be categorical, but Shapley values are numerical. And what's more, in original input space, different features might not be comparable to each other. For example, the number of age and the number of capital loss. But SHAP values make them comparable to each other by calculating the contribution. And the interaction scatter plot shows the interaction of two features on the Shapley values of one feature. And you can visit the SHAP website and documents to explore more by yourself. Here is a summary of SHAP. The advantages of SHAP are quite obvious, right? It has solid theoretical foundations in game theory and naturally dealing with the feature core contribution. The explanation of SHAP is very straightforward and intuitive. It has a directly estimation of feature contribution and can be added up to the predicted values. Also, SHAP has different explainers, including model-agnostic and much faster model-specific version for tree-based models and deep neural networks. and they can deal with different forms of data, such as tabular data, images, and text. Needless to say, its granularity, since SHAP is local explanation, which can be easily aggregated to any level. Still, there are some disadvantages for SHAP. First, even though tree SHAP is optimized for tree-based models and runs very fast, most of other SHAP methods are still slow. It is understandable that SHAP is calculating explanation for each individual instances, but it is not the first choice if you want to get some global feature importance quickly. Second, the model-specific SHAP methods has some usage problem. So you will find different model-specific SHAP explainers have very different arguments and not very easy to understand and use. Sometimes there are strange behaviors and bugs, especially in deep SHAP. It is a little bit unfair to call this degree of freedom a disadvantage, since you can always use kernel SHAP or the most basic sampling SHAP for the maximum stability. The other methods just like give you more freedom to play with, but still, this kind of complexity can make you feel overwhelmed in real applications. So there is a SHAP package available for Python, and there are tons of resources such as documents, examples, and blogs about it. I think for our user, there are also some related packages or methods, but I'm not very familiar with them. And finally, the takeaway. In this talk, we mainly introduced some global and local interpretation methods for black box models, including how they work, some use cases, advantages and disadvantages. And of course, there are way too many methods for this problem. And I just choose some of the most representative ones, which I'm familiar with. So if you want to know more, there are some very good free resources about interpretable machine learning, or refer to the documents or websites of those packages. I hope that this presentation can help you to get more exposure or practice on machine learning interpretation, and you are more than welcome to share your own experience about machine learning in this community. Thanks again for Jens inviting me as a speaker today, and that's the end of this talk. Thank you.
Thank you, Wensheng. And I see we are open to questions. And Wensheng, if you open the chat, there are some questions there.
Okay, yeah, let me check that. Okay. So yeah, I got one question. Is SHAP for images similar to attention in images? And interpretation looks similar, but the mechanism is different. Attention is trained. Okay, so I think like this question has already been answered by Yan. Yeah, I think this is a very good answer, right? Because I mean, attention is actually a mechanism of the model, right? But like SHAPE values is a model interpretation method. So which means it has nothing to do with the model. That's why it's called model-agnostic. It is just kind of like a post-processing, and it can generate some explanation. But the attention mechanism, it will work at the beginning of you training the model, and it actually give you some like inner, I would say like a model-specific inner structure explanation. And also, there's another question: Can SHAP also be used for RGB images which are trained on neural networks? Also, what's the difference between interpretable AI with explainable AI? Okay, so first, for the first question, I would say yes, SHAP can also be used for RGB images, because I mean, SHAP is actually, well, it doesn't care what kind of like model you are trying, right? So it only actually takes the model, the prediction functionality, and the trained data, or some like trained data or test data, and it will just use its own kind of like mechanism or algorithm on the model, the prediction function, the prediction functionality of the model and the data. So of course, I mean, if your input data is RGB images, it can tell you, okay, maybe which color contributes the most to the prediction or classification problem. So yeah, that's the answer of the question is yes. And for the last question, what is the difference between interpretable versus explainable? Well, yeah, so actually I don't have a very good answer for this question. Just like based on my understanding, interpretable can include both, I would say, glass box and black box, right? So for example, like as we say, like the attention mechanism, sometimes you can use this like attention mechanism to interpret the prediction values. So maybe I will call it interpretable. But for explainable, right, it's maybe more focused on the black box model, right? We just use some other methods to try to explain our model or our predicted values or something like that. But I don't think there is a very hard kind of like boundaries or distinctions between them.